Question number 1, you're spinning a bucket attached to a string, could be a rubber stopper in a circle over your head. A, what kind of force holds the stopper in a circular path? Is it centripetal, centrifugal, or I don't know? In a washing machine, maybe you might be familiar with it. Some of you may not have any idea where it is in your house. In a washing machine during the spin cycle, the force is on the water, the clothes, or I don't know, causing the water to be separated from the clothes. Is the force on the water or the clothes? A tube has been placed upon the table and shaped into a 3/4 circle. A golf ball is pushed into the tube at one end at high speed. The ball rolls through the tube and exits at the opposite end. Think mini golf. Describe the path of the golf ball as it exits the tube. So I put it in here. I fire it around like this and it comes out. Does it continue at path A, B? Does it sort of go in between path C, or does it somehow go up and complete? Does it just keep going around and around and around if there was no friction? Does it depend on how hard I hit it? Does it? Which way is gravity? Good question. Gravity is down. Looking at it sort of sideways. I've already asked you this question. In fact, I even think I did 3 revolutions per second, too. Oh, excuse me. True or false on your clicker? I think I've answered this one already too, actually. Do you like the clickers? Hey? No, you don't like them? Too bad. I want to know. Maybe they taught you this in driver's ed, I don't know. When you're driving your car and make a left turn, friction between your tires and the road causes the car to move to the left. You just turn. If you change, when you turn, do you change direction? Yes. When you change direction, is that an acceleration? Yes. So when you accelerate, there must be a force. Which direction is the force? I'm looking top down here. I'm the bird about to poop on the windshield. Are you ready to find out how you did? Oh, we did 68%. That's not bad. You are spinning a bucket. It is a centripetal.
I thought that was the answer because that's on the sheet.
Centripetal. I'm going to give you a sheet right away that explains it.
Yeah.
Centripetal. It's okay if you get it wrong. No big deal. It's the intro one. Don't worry about it. Which is the force on the water or the clothes? The force is on the clothes. How could there be a force on the water? There's holes in the top, right? Which direction will it go? Yes, it will continue out at B. There is nothing you can do to make it go up in the air like that. Is the rubber stopper accelerating? Yes. What direction is the force? In. The force is in. I explained that already. Is this true? It is indeed. In fact, the force is in towards the circle. When you make a left-hand turn, right, you turn the wheels, but inertia wants your car to do what? Like if there was no friction, if you were going on an ice road, as you turn, you go like this, you try to make a left turn, you slide out, right? The reason you don't slide over is because of friction. It's friction pushes it towards the center. Basically, this little handout here explains the entire unit, except for the math part. Okay? It does a real good job of that. You will notice that many of the pictures that were in the little quiz come from the sheet. So after you're done this, you should be able to understand some of those questions from that little quiz. So let's go through it. If you whirl a tin can on the end of a string, this is your brain's going to hurt a bit after this. Okay, so refocus. I know it's Friday. It's about 10 to 3 here. We got about 20, 25 minutes of some solid thinking here, and then I'll leave you alone. If you whirl a tin can on the end of a string, you find you must keep pulling on the string. If you don't, what will happen? It'll eventually just sort of wind down and hit yourself in the head, right? You pull inward on the string to keep the can revolving over your head in a circular path. A force of some kind is required for any kind of circular motion. Any force that causes an object to follow a circular path is called a centripetal force. You'll notice that I've highlighted. A centripetal force is any force that causes an object to follow a circular path. Does it need to go in a complete circle? No. Is projectile motion a form of circular motion? Yes. Centripetal means center-seeking or toward the center. The force that holds the occupant safely in the rotating carnal ride in figure 13.1, which I don't have up there, is a center-directed force. Without it, the motion of the occupants would be along a straight line, and they would not revolve. Now, when the fair comes to town, who gets in that little ride? You walk in and you stand up. They put that little flimsy little chain across you and you hang on. What's that thing called? G-force. I'm not going in. But, does anyone here go in? Yeah, you like that? Why do you go in there? Okay. What does the little ropey thing do? Absolutely nothing. It's there to make you feel better. Yeah, I feel better. What am I going to follow? There's a little 1/4-inch line of rope holding me in here. Right? Do you need to hang on? No. What holds you in place as you go? Force. Is it centripetal force or centrifugal force?
I don't know. G-force.
G-force. What does that mean, G-force?
Force of gravity.
Gravity? Force of gravity? Well, it's really inertia, right? If you are driving down the highway, right, and I don't know, who's the worst driver here?
Not Zach.
Okay, and someone cranks the wheel, Zach cranks the wheel. Joey's had a few accidents, right? Let's say I'm driving you guys in a big bus, we're going down the highway, and I crank the wheel to the right. Everyone goes which way? To the left. How come? Inertia. Objects in motion, right? Same thing with the G-force. You're spinning around, you're trying to go in a straight line, like the rubber stopper going in its head, but a force is holding you in there. Now, when I whip the rubber stopper over my head, clearly the force is through the tension in the string. What's the force holding Heather in the G-force? Because there's no strain from the center towards you. The metal? Is it towards the center? It's an interesting concept to think about. I'm not going to sort of explain it just yet, but I'm setting you up. I might be able to find something. Centripetal force is not a new kind of force. Okay? Guys, I know it's Friday. Please listen. Ryan, are you with us? Okay. Centripetal force is not a new kind of force. It is simply the name given to any force that is directed at right angles to the path of a moving object. That's key, and I should highlight that. That part that I just read. Stay with me here, you guys. I know people work Fridays. Centripetal force is simply, whoops, that's not what I wanted. I want to highlight that. Simply, any force that is directed at right angles to the path of moving an object tends to produce circular motion. The force is at right angles to the path, 90 degrees. Gravitational electric forces act across empty space as centripetal forces. The Earth holds the Moon in orbit through gravitational force. Gravitational force directed toward the center of the Earth holds the Moon in an almost circular orbit. Look here. Electrons that revolve around the nucleus of an atom are held by an electrical forces directed towards the center. Centripetal. Centripetal force plays the main role in the operation of a centrifuge. A familiar example is the spinning tub in an automatic washing machine. In its spin cycle, the tub rotates at high speed. The tub's inner wall exerts a centripetal force on the wet clothes, which are forced into a circular path. The tub exerts great force on the clothes, but the holes in the tub prevent the tub from exerting the same force on the water in the clothes. The water therefore escapes. It's important to note that a force acts on the clothes, not the water. The force is pushing the clothes in a circular path, and it's the water that's going in a straight line. Can you give me another example of that type of system? You probably have one in your kitchen. I have one. The salad spinner. You wash the lettuce, you throw it in there, and you crank it right, and it spins around, and there are little holes on the inside thing. Yes, the force is on the lettuce, not the water. The water does what? Goes straight out, straight line path. They use these in biology too, a centrifuge, to separate the blood, right? They spin it around and they separate it. No force causes the water to fly out. The water will do that anyway, as it tends to move by inertia in a straight line path, Newton's first law, unless acted upon by a centripetal or any other force. Excuse me. So interestingly enough, the clothes are forced away from the water and not the other way around. When an automobile rounds a corner, the sideways friction between the tires and the road provides the centripetal force that holds the car on a curved line path. If the force of friction is not great enough, the car fails to make the curve and the tires slide sideways. The car will skid. Right? So as you go around a corner, it is a centripetal force provided by friction that causes you to go in a circular path. And if your tires aren't very good, there's not enough friction and you slide over. Centripetal force. Okay, so what's this centrifugal force then? Because you quite often hear people, maybe not quite often, at sometimes hear people talking about centrifugal forces. Turns out they don't know what they're talking about. It's not. It's just that they don't really understand. So you are, again, becoming part of a knowledgeable gang of people that know better. In the preceding examples, circular motion was described as caused by a center-directed force. Sometimes an outward force is attributed to circular motion. This outward force is called centrifugal. Outward. Centrifugal. Centrifugal means center fleeing or away from the center. In the case of the whirling can, it is a common misconception to state that a centrifugal force pulls outward on the can or rubber stopper. As I spin it above my head, is there a centrifugal force on the can? Rubber stopper? No, there is a centrifugal force holding it into the circle. There is no outward force.
So what is an example of centrifugal force?
We'll talk about that. Now, if I could shrink Zach down and put him on the rubber stopper, and he, sat there, and I spun him around, would he feel a G-force? Oh yeah. Oh yeah. Would he feel a force? Yes. Where does that force come from? Because when I pull it on the string, pulling it towards the center. Zach feels, if he was like, he'd be like, if it was like a glass balloon, he'd be smushed up against the wall of the bus kind of thing. If it was an actual school bus.
He'd be feeling the force that is coming inward, say, if he was on top of it, the force is coming inward.
It's,
On him.
yeah. It's kind of like normal force, weight force, right? Like when you're standing, do you feel the force on your knees? You don't, because we're used to it. But if you jump from a height and you landed, you'd feel the ground pushing up on you. That's what Zach feels. It's not an outward force, it's an inward force. It's kind of opposite to our ideas, our sort of the way we think about things. Yeah, I know. Magic School Bus is awesome. If the string holding the whirling can breaks, it's commonly stated that a centrifugal force pulls the can from its circular path, but that is not true. In fact, when the string breaks, the can goes off on a tangent straight line path because there is no more force acting on it. And objects in motion stay in motion. See if that whole thing about people don't really get Newton's laws. Suppose you're in the passenger of a car that suddenly stops short, right? Stops quickly. You pitch forward against the dashboard. So you're driving down Main Street, Zach's driving, he sees Mr. Bennett rush across the street, and he slams on his brakes because he doesn't want to run Mr. Bennett over. Brady goes head first into the dashboard. Ice cream cone right to the nose. How come? Because Brady wants to keep on going forward at the same speed he's going, right? When this happens, you don't say that something forced you forward. You know that you pitched forward because of the absence of force which a seatbelt would have provided. Similarly, if you're in a car that rounds a sharp corner to the left, you tend to pitch outward to the right. Right? Driving the school bus, I crank the wheel to the left, you all go to the right. Not because of some outward or centrifugal force, but because there is no centripetal force holding you in circular motion as a seatbelt would provide. The idea that a centrifugal force bangs you against the car door is a misconception. So when you swing a tin can in a circular path, there is no force pulling the can outward. Only the pull by the string acts on the can and pulls the can inward. The outward force is on the string. Notice that it's highlighted. As I swing it around, I provide a force in on the rubber stopper, but the rubber stopper, is it pulling on the string? Yes, it is. So there is an outward force, but it's on the string, and that's provided by inertia. It's all very short. Like, oh man, it's Friday afternoon, I don't want to think about this, right? Now, suppose there's a ladybug or a very small Zach inside the whirling can. The can presses against the bug's feet and provides a centripetal force that holds it in a circular path. The ladybug in turn presses against the floor of the can, but neglecting gravity, the only force exerted on the ladybug is the force of the can on its feet, as Ryan was saying. From our stationary frame, outside stationary frame of reference, we're all watching Zach whirling around inside the little tin can. Right? Go Zach. We see that there is no centrifugal force exerted on the ladybug, just as there was no centrifugal force exerted on the person who lurched against the car door. The centrifugal force effect is attributed not to any real force, but to inertia. The tendency of a moving body to follow a straight line path. Try telling that to Zach or the ladybug. He feels the force pulling him in. Now, here's where this is the, never mind, I'll explain that some other time, yeah. Okay. Now, if you're inside the can, then things are a little different. Our view of nature is very much influenced by the frame of reference from which we view it, right? It's all dependent upon your frame of reference. I'll try to wrap up in the next few minutes because I can see that I'm losing it. When we sit on the seat of a fast-moving train, we have no speed relative at all to the train, but an appreciable speed relative to the reference frame of the stationary ground side. We've just seen that in a non-rotating reference frame, the force that holds an object in circular motion is a centripetal force. So we're outside the spinning can. We are in a non-rotating reference frame. For the ladybug, though, the bottom of the can exerts a force on its feet. No other force was acting on the ladybug. Nature seen from the reference frame of the rotating system is different. In the rotating frame, in the can, in addition to the force of the can on the ladybug's feet, there is a centrifugal force that is exerted on the ladybug. Centrifugal force in a rotating reference frame is a force in its own right as real as the pull of gravity, but only inside the rotating frame of reference. There's a fundamental difference. Gravitational force is an interaction between one mass and another. The gravity we experience is our interaction with the Earth. But centrifugal force in the rotating frame is not part of the interaction. It is like gravity, but with nothing pulling. Nothing produces it. It is the result of rotation. For this reason, physicists rank it as a fictitious force. It is not a real force like gravity, electromagnetism, and nuclear forces. Nevertheless, to observers who are in a rotating system, centrifugal force seems to be, and is interpreted to be, a very real force. Just as from the surface of the Earth we find gravity ever present, so within a rotating system, centrifugal force is ever present. You've probably seen space movies. We started watching that series, The 100, at home.
Can we watch the Rocket Man?
You watch Space Jam?
Oh, that's the
Yeah.
new one.
You
Come on, 1997.
Space Jam?
Oh, Rocket Man.
Rocket Man.
Come on.
No, I don't get it.
It's 97.
I know.
What was that movie with, like, where they go, like,
Great.
space mining or something?
Space Mine, like with Bruce Willis?
The guy from the Green, yeah, with Bruce Willis, the guy from the Green Mile.
Yeah, 'cause the asteroid is going to hit the Earth.
Yeah, what's it called?
Heat impact? Or Armageddon?
Armageddon, that's it.
Armageddon. Great movie.
Is that the one?
When you see those space movies, quite often you see, like we're watching that 100, right? And the International Space Station, when you see the astronauts up there on the International Space Station, are they sort of floating around? They're basically weightless, right? But when they put them rotating, they sort of create like a fake kind of gravity. And I remember seeing that on that show. These people are walking around the space station, no problem at all. It's like being on Earth because it's rotating. But as soon as they step outside into space, well then suddenly they're weightless, right? It's complete and utter physics fail. Don't you hate those people from movies that yell out physics fail in the middle of the movie?
No.
Oh, that's just me that does that.
That is not a thing.
That's not a thing?
Good try.
Oh, one of these days I'm going to see it in the movie and I'm going to yell physics fail. And you're going, oh, man, shut up. I have 2 questions for you. They are not easy. And then we're going to try to convince Tatiana to do something.
What am I doing?
Launch the
You're
rocket.
qualified to do it. You're the only one here qualified to do it.
Launch the rocket.
No. Well, you might not be the only one, but you're the only one that I know is qualified. We'll find out right away. I want you to think about these 2 questions, and then we're going to answer them right away. There's the answers. Oh yeah, and then we're going to talk about helium balloons in a car.
What is the wrong answer?
When you were a kid, right? You still do that? Zach, if you want to go faster, do you go towards the center or do you go to the right to the edge? In fact, some kids even do what? They go even faster. Hang out. Hang out even farther, right? And if you're sort of one of those people with a weak stomach, you go towards the center where it doesn't quite go as fast. Okay, so think about this. Give me just a couple more minutes here, you guys. A heavy iron ball is attached by a spring to a rotating platform, merry-go-round, as shown in the sketch. 2 observers, one in the rotating frame, that's the man, and one on the ground at rest, non-rotating frame, observe its motion. Which observer sees the ball being pulled outward, stretching the spring? Which one sees the spring pulling the ball in a circle? So I'll ask you the first one. Which observer sees the ball being pulled outward, stretching the spring? The guy at...
Or the girl?
Well, the lady's at rest and the guy's on the rotating frame.
Which one sees it being pulled outward?
Which one sees it being pulled outward?
The man. Down the middle.
Well, just go ahead and read that.
I don't understand.
It's upside down on yours. You can read it if you want. You don't understand it? It says, oh, I gotta get into the light. The observer on the reference frame of the rotating platform, that's the man, states that a centrifugal force pulls radially outward on the ball, which stretches the spring. The observer in the rest frame, that's the woman outside, states that a centrifugal force applied by the stretch spring pulls the ball into a circle along with the rotating platform. So she sees the spring applying a force to the circle. He sees an outward force pulling the ball outward. Can't really explain it. Right? You're right. He wouldn't really see a circle. If he was just, if it was walled in, all he would see is this ball being pulled outward for some mystery reason. Right? The rest frame observer, that's the woman, can state in addition that the reaction to this centrifugal force is the ball pulling over on the spring. The rotating observer, interestingly enough, can state no reaction counterpart to the centrifugal force. He sees the action force, but there's no reaction force. I thought Newton said that for every action there must be a corresponding reaction. Not true on a rotating reference frame. Why are you doing that now? Question number 2. The spring in the sketch is observed to stretch 10 centimeters when the ball is midway between the rotational axis, the post in the middle, and the outward edge of the circular platform. So the string is stretching out 10 centimeters. If the spring support is moved so that the ball is directly over the edge. So in other words, if, here it is right now, right? If I move that center post like that, so now the ball is sitting right on the edge, will the spring be stretched more than, less than, or the same 10 centimeters? Will the ball will be farther away from the center? Will it be traveling faster? Slower? Does it have to travel a longer distance?
Faster, yeah.
Yes, in a shorter amount of time? Faster. Right? So will it stretch more?
Yeah.
Well, the answer's there at the bottom.
Yeah.
The ball will have twice the linear speed at twice the distance from the rotational axis. The greater the speed, the greater will be the centrifugal force, which will also be twice, stretch the spring 20 centimeters. And in fact, the ball will go off the edge. Okay, I got a video for you. Have you ever played with a helium balloon? Yeah, they can be a lot of fun. I don't have a helium balloon, I'm afraid.